In 2011, a new micropatterning method were introduced by Leibniz. I want to review this paper. A new micropatterning method of soft substrate revealed that different tumorigenic signals can promote and reduce cell contraction levels. First, they introduced their research background. Geometrical and mechanical properties of cell microenvironments have a profound impact on cell morphogenesis and functions by modulating the forces produced by cells, especially affecting the orientation of contractile stress field and the location of the force application sites. The subcellular location of traction force affects intracellular organization, notably centrosome positioning, primary cilium growth, and intracellular trafficking. Micropatterning techniques were used to manipulate the localization of adhesive molecules from the extracellular matrix and thereby control the position and shape of individual cells. To investigate whether high levels of cell contraction are systemically associated to tumoral transformation, they took advantage of their new micropatterning method of PA to orient cell traction forces and impose them to perform a standardized exercise. In result, they explain how to fabricate new micropatterning method on soft substrate. The substrates were directly exposed to PA with deep UV and after coated with fibronectin. To prove their new method, MCF10A cells, which is non-tumorigenic human epithelial cells from the mammary gland, were used. The cells were attached on the specially exposed region. To confirm the effects of micropattern geometry, they make the various patterns like disc, Pac-Man, and crossbow. The orientation of cell traction forces were measured by looking at the displacement of fluorescence beads. By measuring force field exerted by individual cells, they could analyze the controlled localization and focusing of force application sites. In details, there were randomly distributed forces on no-pattern substrates. Cells on disc patterns show still randomly oriented but lower magnitude than that of no pattern due to reduced cell spreading. Pac-Man's shape made the cells to have geometrically biased force distribution. At last, cells on crossbow shapes showed more simulated traction forces due to enhanced cell contraction above non-adhesive regions. From these results, appropriated micropattern geometries can both stimulate cell contraction and orient force application. Next, they checked the force field streamlining to allow reproducible force deformation relationship. The local deformation could reveal the total amount of contractile forces when all actin cables are oriented toward a single point, as it is the case on crossbow-shaped micropatterns. The force deformation relationship in micropattern cells were analyzed on 4 types of geometry. Especially in case of crossbow, there was good linear correlations between force and deformation. To validate force measurement, well-described blebbistatin, which is myosin II ATPase inhibition effects on cells contractility, were used. Cell traction forces in response to blebbistatin were calculated on crossbow-shaped micropattern. The force inhibition profile upon increasing dose of blebbistatin matched the myosin II inhibition profile and the cellular force profile. Drug effects on cell contractility could thus easily and rapidly be quantified using this new methodology. Also, force magnitude decreased in response to 50 micromole of blebbistatin following single exponential decay. The last results show that all tumorigenic transformations do not increase cell contractility. Contraction level of wild-type MCF10A cells versus drug-treated or genetically modified MCF10A cells mimicking various forms of tumoral transformation were measured. Cell contraction levels measurements could help in the diagnosis of cancer progressions and allow the development of new and improved treatment. Cells were exposed to TGF-beta, ERBB2 receptor activation, and protein kinase CK2 inactivation. With two characteristic tests of tumor-like behavior, anchoring independent growth and inability to self-assemble into acini-like structure in 3D matrix, they confirmed that their treatment conferred tumoral feature to MCF10A cells. Cells exhibited a significantly higher level of cell contractions as revealed by crossbow shortening. Different treatments or inducing tumor-like phenotypes could either promote or reduce the level of cell contraction. They also demonstrate that their method can easily be used at large scale to more precisely characterize this complex correlation between cell contraction and tumoral transformation. Deep UV exposure on PA in contact with the photomask is the most robust and easiest method to create homogeneous and reproducible micropatterns on soft deformable substrates. New protocols to recapitulate actual in vivo conditions for cell anchoring. This method is adapted to provide an easy and fast measurement of the global cell contraction level with only a simple local measurement. In other words, this method paved the ways to large scales and high throughput analysis of cell contraction states. It would be now necessary to more specifically analyze cell contraction levels at various phases of tumoral transformation to clarify the relationship between cancer progression and cell contraction. In conclusion, this method could have a broad range of the application, notably in the design of new biomaterials for tissue engineering purposes. It can also be applied to the quantification of global cell contraction levels via the simple measurement of micropattern deformation. Not all cancer cells are more contracted than normal cells, and that cell contraction levels may vary depending on the nature of the tumorigenic signal or the stage of cancer progression.